graduate and you have questions on homework, or
That's
you're
not what I wanted. Hello, hello. Oh god, I'm turning into Eric. Do you have both up right now? Yes, it is. Yes, yes, it is. How are the levels, Jax? Audio? Visuals? Oh wow, that's very fast. What is it? What is the use for this? Not much use, just fun to look at. Which is pretty much the only reason why I make anything. Put a note on Discord. You know, that's probably a good call. Let's see. Why did I just say that? The British are coming. Thanks, Jax. Hey, look at that. Welcome, raiders. Thanks, Eric, for the raid. Highly appreciate it. Yahoo! And welcome everybody else. Thanks for the follow from Idiots for Idiots. I love the name. And look at that. You all get to see our brand new follower alert image. I just made that last night, and I'm pretty proud of it. Yahoo! Some actual work went into it. Thank you, Mayrono3. Oh, still loading. So slow. I mean, yeah, we tried to cook an egg on your processor the other day, so. Okay, well, welcome everybody. If you don't know who I am Non-Dairy Neutrino, or as some of you may know me, NC from Eric's channel. And kind of the goal and theme of my stream is to actual work didn't you copy paste from the internet? Okay, some of it, but the actual math part I copied, but the rest of it is all me. Yes, Mathematica. I would say the only area that I am even close to an expert in. But yeah, the kind of idea here on this channel is to teach and provide some sort of entertainment about Mathematica, because it's a great resource in science, and it has so many capabilities that I've come to love over the years. And I know over my time in school, I saw a lot of people that would like to use this program and this language and things, but like didn't know where to start and stuff like that. And so I wanted to provide a resource to people out there, an interactive resource, especially in this time of distance learning, to be able to, excuse me, to be able to learn this and be able to ask questions. Questions are welcome, of course, down here. You can see that. And yeah, and I like doing this. I like teaching. I like writing code in Mathematica. And so I hope you enjoyed me enjoying it. So Jax, I love that NC has become your only name, and everyone always asked about the binary digits and not what NC actually stood for. Right. Yeah. You referred to me as Nate earlier, and they were so confused. Yep, that checks out. Usernames exist for a reason. Yes, welcome everybody. If this kind of stuff, if looking to see what goes into, or the thinking and math that goes into making this animation try to look like this animation over here, then you're in for a treat, because that's the exact goal of today. So, the first thing we're going to do is maybe kind of go over the first part, maybe a little freeform. Thank you for the follow, Mixurio. I hope you're having fun regardless. But yeah, the first part is kind of going to be going over the code and math that goes into representing what this is, and then also upgrading it and revising it. I wrote this code and made this animation quite a while ago, and you know, just looking at it with fresh eyes, I can immediately see where some things can be made more efficient, or at least more compact, and I think just all around better. So that's what we're going to be kind of doing, and in the process kind of showing what conventions are better and explaining why and things like that. So if you have any questions about what I'm doing, or really any question at all, feel free to ask at any time. So why don't we start? So this animation over here, this one, is an animation I came across on the internet a long time ago, and I thought, oh hey, that looks really cool, and it looked like it would be really doable to implement in Mathematica. And so I said, okay, well, let's do it. And so my first thought were, okay, so we have, I'll put that in screen so you guys can see it. We'll crank up the music a little bit. And so, okay, well, we have a kind of a circle of points around, and then lines, and then a square made of points inside. And it initially, my brain interpreted it as, okay, the square is rotating, and the lines coming from each of the points on the circle are going to the nearest point on the rotating square. And so I said, yep, that's exactly what it's doing, and then ran with it. And then so I made this, which is exactly that. But then on looking back, I realized that in this animation, I'm gonna make it a little bigger. And then I realized in this animation that the points are not actually, or the square, the points that compose the square are not actually rotating, but rather they're just moving in tiny little circles. And so that's what we're going to try to do with the accurate recreation part of this kind of other notebook. But first, let's try to make this original a little bit better. So, we'll start with the math. So the idea here is, okay, let's make our circle of points and our square of points. Okay, well, what's our circle of points? Let's call that circ points, and let's practice prudent programming. So let's come over here, and we say, okay, clear all of our kind of points variables. And we're going to go over there, and then we're going to say, okay, well, how do we make a bunch of points on a circle? Well, we can do this, and so basically what this is saying is that, okay, give me a list of points starting from 0, ending at 2 pi, and in steps of pi over 16. So what this does is it gives us, okay, 0, pi over 16, pi over 8, or 2 pi over 16, and then so on and so forth, up to 2 pi. And so that's what that is. And then we can say what this thing, or, well, let's start with this over here. And so what this is saying is that, okay, this is kind of a function that doesn't have a name. And so just because we're only going to use it once, we don't need to give it a name. And so basically, this takes in a value and puts it inside the cosine and sine. And so what this does is we can just kind of come over here, and then we can say, okay, we want to, because we don't want to kind of write the same thing twice, and so that's why we anonymize the argument and then only have to write it once, and then it'll be just put into everywhere it goes inside the function. And so, okay, we just want at an arbitrary value, and so we'd say, okay, we want this of t. And so now I only have to write t once, and it goes into both. And so then it gives me the vector cosine sine, which is the position on the unit circle. And so now we can say, okay, so so this gives us the position at some argument on the unit circle, and then this is all of the angles that we want our points at. So how do we put all of these into here? Well, that is what this guy is for, this little slash at. This is the map. Well, it's the shorthand for map. And so basically, it kind of, in my head, it does what you want functions to do. So basically what the difference is that, like, okay, let's say naively, we want to get a list of points, and we just throw the whole list of these angles inside our function here. So Jax asks, I was about to ask, can't you shorten that whole array? I'm not sure what you mean. Which array? Let's just throw it in there and see what happens. Okay, so now we get a list of 2 lists, and each element in that list is kind of, well, really what it's doing, if you follow my explanation from before, is that it's passing this line of code, is saying, okay, take this and put it into cosine. But cosine has the property, which we can look at with attributes, cosine, and it has this listable property here, or rather attribute. So Jack says, sorry, my eyes are breaking. I thought you had typed out all those fractions manually. No, I did not. He said, make the computer do it for us. I'll have the animation there for it. Well, I need to see the code. And so what happens is that since cosine has this attribute, listable, is that when you give it a list, such as this list, then it kind of threads the function through that list. And so, and basically, okay, what does that actually look like? Let's say cosine of 1, 2. That gives me the list of cosine 1 and cosine 2. Okay, so Formidiots says, I'm hoping to sweet Jeebs I can find a Mathematica tutorial which my tiny brain can understand. Well, hopefully this is it. Hopefully the ability to have a dialogue between yourself and me can give you some sort of insight. I can answer a question or kind of reinterpret things instead of a very one-sided learning experience, which I found seems to be the most prolific way of doing it, of learning this out there. And so, yeah, I hope this is exactly what you're looking for. But yeah, so going back, so this is what happens when we give cosine a list. It gives us a list of cosine evaluated at the corresponding, excuse me, evaluated at the corresponding values in the corresponding positions. Like, because then this would also give us cosine 2, cosine 1. And so if we kind of combine this knowledge along with, so combine the listable effect with the function effect, then what this is doing is saying this first list is cosine evaluated at each of these points. It's a list of cosine of 0, cosine of pi over 16, cosine of pi over 8, so on and so forth. And then likewise with sine. But that's not what we want in this instance. And so another way, or one way of getting what we want is by using this kind of operation right here, which is called map. Yes, we do have a Discord, and you can check that out with the Discord command. And yeah, you can ask any questions there. We have a good few people in there, and I'd be happy to talk more. Okay, so this list of lists is not exactly what we want. We want a list of kind of points all around the circle. And so basically we can say, okay, have this, and then this kind of, I actually think about it kind of visually. It takes this function and it jumps off this ramp, kind of, let me zoom in a little bit. It takes this function and kind of like, this function is coming in from the left, and then this ramp is propped up by the @ signal, or the @ symbol, and then it kind of jumps off, it bounces off of this, and then hits over to each element of this list. And so it's like, it comes in and it goes, and it goes boom, 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 and then it hits every element, and then it gives us exactly what we want. So really what this is giving us, let's bring this back down. So MS says, if you show it with table form, it might be easier for us viewers trying to look at where the brackets are. That is a good point. I see. Someone has some experience. Well, let's make this. So we can view this kind of list of lists as a matrix or a table or a grid, or there's many different words that are all slightly different. But so we don't want kind of this kind of 2-row thing. We want kind of the columns. And so probably what you're thinking is, okay, we'll just transpose it. We can do that, but that's not what I wrote here. And I'm explaining what I wrote here. And that's actually what I'm going to be putting in a second, but I'm explaining this code here. So anyways, but yeah, basically, so yeah, if we take this and we say, oh, okay, let's bounce this function across each angle that we want, and then we get exactly what we want. And, thanks, Joe. I do like the music. And so what we can do is, so this is what we want. And so we can look at this with a table form, and then that's kind of, I think, hard to read. So let's do a matrix form. And so not much better, but so now we have a list of 2-element lists. And so that is kind of our list of points. Okay, Jax, it looks like it's pretty late your time. And so hopefully we will have fun, and we'll see you next time. So now that we kind of know what's going on here, we can rethink about it and try to improve upon the efficiency and kind of use the built-in features of these functions, sine and cosine, namely this listable attribute, to kind of compactify the code and make it a little more efficient in runtime. So really what we're going to do is in our notebook over here, which is actually, I'm going to take all of this and we're going to put it up here. We're going to go like that. And so what we're actually going to do is say, okay, we basically want this, except now we're going to take advantage of the listable nature of the trig functions and say, let's just get rid of that. And then, so now that'll give us this thing, but we don't want that. But as I noted before, we can just transpose it. And look at that. It gives us exactly what we want. And so now we can, okay, so now we have our points on the circle. And so now I think we can get rid of this. So now we have our points on the circle. And then we don't actually want to look at it. And so we can just say, put a semicolon there, and that tells Mathematica to do the operation, but don't show it. And so we can just say that. So Doe asks, that's just a matrix transpose, right? Yes, that is correct. Transpose is, yes, it's effectively the matrix transpose. This transpose can actually also work on higher rank tensors, which is something that we may talk about at some point, but certainly not right now, because we don't need to. Okay, so the next step. So now it's on to, so let's be good programmers and document our code and say points that make up the circle. So it's just some command you're giving Mathematica. Yep, transpose is saying this operation right here is saying, okay, everything to the left of these slashes, minus this part over here because of priority reasons, pass that to transpose, and then it just flips everything. So in the Wolfram language, from idiots, the slash the double slashes is not in fact a comment, as you may see it in other languages, but rather it's another kind of operation. The double slashes is shorthand for what's called postfix. Right. Yeah, thanks, MS. Right. And so the different ways of writing things correspond to how you want to prioritize kind of groupings and positions within your code. And so I'm doing it this way because I don't want to have to put a transpose in the front and then wrap everything in square brackets. And so I can just say, okay, everything over here, transpose that. Okay. And so now, let's make a square. Let's make a square. Okay, so what is a square? Or rather, how do we write the side? How can we think of the sides of a square? As question for chat. This is an interactive stream, anyways, right? It has 4 segments, yes. But what kind of segments? How are the segments oriented? 4 equal length sides, yep. But are those sides in any particular so 4 equal length sides, 90 degrees from each other, orthogonal, yep. At angles of 45 times 2 is 90, yep. But yeah, okay. So, kind of a read my mind question, but very basic. The sides of a square are parallel line segments. Well, not every. The sides of a square can be formed by pairs of parallel line segments that meet each other orthogonally. Same distance from the center, yeah. So yeah, I think all of those things together form the statement of the parallelism. Okay, and so that's kind of what I was going for here in these left points, right points, or left points and right points. And so this has the same form as up here, so I'm not going to go over it again. And since it has the same form, we can do the same thing by taking advantage of kind of attributes of functions. And so we can say, oh hey, let's take kind of these coordinates. Well, let's take this whole thing. So let's kind of take these coordinates, and so here I'm stipulating that the kind of x coordinate is -½ and then I want a list of y coordinates to place each point at. But so we don't actually need this map, we can just say, oh, and we actually don't need that function either. We can just say like that. But then that won't actually give us what we want. Let's undo that and then bring this down here. And so that'll give us this, and that doesn't make any sense. We don't want that. But what we can do is that Mathematica has this function called thread. And for our intents and purposes here, that gives us, that kind of threads, it pushes through the kind of list structure with this first element to each point in the secondary list. And so, instead of mapping a function over a list, we can just kind of take advantage of the automatic properties that happen. so we can just say that. And then likewise, we don't want to look at it, we can do so with the right points. So same thing. And so that's basically, well, as we can see here, each point is at positive of 1/2, and then say negative half, and then another point at positive half, and then up a little bit. And so we just have on the quote-unquote right side of the square a line of points, or all points on a line, going straight up, being vertical. Another way you could do this is, instead of having left and right points, you could make a sequence of points and then just rotate that 3 times. So, well, let's try to do that real quick. So let's just take our kind of list of points here. And so, okay, what does this give us? This gives us, like in our heads, let's stop this. So this list here gives us this line of points on the left. This is left points after all. But then, okay, we don't want to make a bunch of different lists. We want to just work with this one list. And so, but how do we go to how do we get from this list to this list and this list and this list of points? Well, we rotate it. And so what we can do is say, okay, well, let's actually, but we don't want to overlap points. And so what we're going to do is we're going to neglect this kind of thinking about this sequence of points. We're going to neglect this one, because when we rotate it, this first point will go to this point over here. And so what we can do is say, okay, let's rotate all of these things by, what's 90 degrees? Pi over 2. And then using this command, this is kind of going to take the inner product, or have this rotation matrix act on this list of vectors. And so that will give us, I guess, just to kind of show the sequence of thought here, we can say, oh, well, that doesn't work. And so, because the dimensions are right. And so, in this instance, I'm confident there are some vector arguments that you could make, kind of transitioning or transforming this matrix into a higher dimension to be able to just straight act on it, but I'm lazy, and so let's just map it over. And so if this, well, actually, here you go. So if this is, let's not take that, but let's work with left points here. And then, okay, well, if we take all of these left points and then rotate it pi, then what do we get? We should get right points. And do we get right points? No, we don't. Because so if this is left points, what is right points? Oh, right. We don't get right points, but what we get is the reversed set of right points. And so we can say, okay, And then, so we want to just reverse the ordering of that list. And so then we say, okay, does that equal right points? Yes, it does. And so this is our first step in actually seeing that we can just rotate one side 3 times to get all 4 sides of the square. And so what we can do is say, let's take left points, and I always forget, we want to drop the last element, and so we use most. And so we come over here and we say, okay, do that, and then so we want to rotate this kind of sequence, this list of points here, and then we want to go boom, and we want to rotate it pi over 4 to get this side. And so now we have so originally we're working with this point through this point, and then we rotate it, this corner becomes this corner, and it goes over to here, and then we rotate it again, and then this corner becomes this corner, go down, and then this corner becomes, or this corner becomes this corner, and we go through, and then we have a full square. So what we can do is get rid of this, and we can say, okay, well, we want to do that 3 times, each one being another integer multiple of pi over 4 as the rotation angle. And so we can say, in this instance, since we want our indexing variable to be k, we can use table, which is kind of like well, it creates a sequence, more or less. And so we want, okay, we already have our first points, and so we just want to start with 1 rotation. Okay, so for MIDI it says, what does k do? So k, if we give it 1 second here, so this, what this does is it's saying, okay, take this expression and then evaluate it however many times, evaluate it at implicitly k equals 1, and then k equals 2, and then k equals 3. And so now this should give us 3 lists of points that are all equal to the left side of points rotated by pi over 4, or pi over 2. Yes, for many, it's so a way to iterate. Yes, yes, yes. Yes, think going from a conceptual kind of way of thinking about it to an actual or mathematical way of thinking about it to more of a computational way. Okay, and then water time. Do you are right? Well, okay. Is K just a Mathematica thing, like programmers use I? Yes. Though you don't need to use K, you can actually just call it anything, and that's the beauty of table here, is that we could use I, and then put I here, and then it does the same thing. You can call your iterator whatever you want. I just like to use K for personal preference, as my choice of iterator symbol. And so now, if this gives us our kind of top side, right side, and bottom side, then to make the whole square, we just need to prepend this list, this given list, with our left side, which is really just this. And so kind of a way to do that is, granted we're doing more work, but kind of compactifying our code here is just to take this list, which is what this is referencing, this percent symbol, this previous output symbol, and okay, put it in here, and then for k equals 0, rotate it by that angle. But k equals 0 makes this angle, the rotation angle, 0, which is really not doing anything. And so, okay, it just spits out the list itself. And we actually don't need this reverse because that was just a way to get the equality from before. And so what we can do is we can actually just take that, and we don't need to have it up there anymore, and we can just do that. So now we have our left side and our, well, here, let's make this a matrix. And so now this top row is our left side of points, and then this is our top side of points, and our right side of points, and our bottom side of points. And so we can see that if we come down here and we say, well, that would take a minute to actually show you, but I'm confident it is. Any questions so far? So we can let that go again. And so, okay, now we have the points that make up our square. And so let's unimaginably call them square points. And practice prudent programming and say, oh, let's just keep those. And we don't want to look at it. But first, what we're actually going to do is that right now this is a list of a list of lists. And we don't really need to make the distinction structurally in this list or computationally that each of these forms a different side. Because all of these points are kind of just, they're just points in and of themselves. And so what we want is really just a list of points by themselves instead of a list of lists of points. And so what we can do is we can say, do that, and basically what this is saying is, well, we can do that, or we can just say catenate. And then basically this function takes a list of lists and gets rid of the inner one. Or basically joins all of the inner lists. Right, Doe. So we just needed to get rid of the nested list. And so we can see that's exactly what we did here. And so now we just have a list of points, which is exactly what we want. And so we can do that. And so now we don't even need, well, I guess we do need left points. Okay, so if this is circ points, we don't actually need these anymore. We don't need right points at least anymore. And so we can take this and we can actually highlight this cell and then come up to this cell and highlight this cell, and we could say merge cells. And then Mathematica just automatically takes both of those cells and then squishes them together. So now we have, and we can get rid of that because we already are clearing square points and we don't need right points anymore, but we're going to run it anyways so we can get right points definition out of the system. And so then we can let's document our code. And then just to be consistent, left side of the square. And then we can say rotate the, I can spell, I swear. Rotate the left side, or most of the left side. Most of the left side of the square to form the rest of the square, of these sides. Okay, and then so we can just throw this comment in here, and catenate will just skip over all of it, and it will still act upon the table. Okay, so that's our square. But now we have the points in our square, and now, how do we rotate that square? Well, we kind of do the same thing. Sorry for all the pauses, I just cough a lot, and so I have to mute myself, and so I don't blast all of your eardrums. I'm also sorry if I miss any follows. It doesn't actually make a sound on my end. That's something I think I just have to fix. And so, yeah. And so I only am notified if it comes up in chat or I happen to be looking at OBS. But so, now we have all of our points that make up this square. And now we want to, in an attempt to recreate this thing, but better, using better code, we rotate that whole square. So, using the same idea of rotations, we can, now down here, say, okay, well, now let's make a function, and then, or I'll say, another way of thinking about rotating the whole square is rotating each point that forms the square by the same amount. And over here, we kind of have that idea, rotation square. And so much like before, right here, when we're kind of mapping our rotation matrix to each of the points or the vectors, we can do the same thing, because I don't want to think about how to transform the matrix to how to vectorize this operation and make it act on each of the points in and of themselves, because it's already quick enough. And so what we can do is say, okay, well, we want to rotate each point on the square, so let's get a rotation matrix. Rotate matrix. And we want to rotate it by some arbitrary angle, say t. And then we want to act on each of the vectors. And we want to map that over each point that forms the square. And, well, what do we get? We get each point rotated by an arbitrary angle. So for idiots, it says, do all the dots rotate the same way? I'm not, there are a few ways to interpret that question, so I'm not exactly sure how to answer, but, well, yeah, I don't want to add confusing information. Oh, they do, okay. So again, the idea that we're doing here is to recreate this animation right here. And then later we will be recreating this other one over here, because they are in fact different. Which was not immediately obvious to me, which is why I made this one first. But yeah, and so here are all of our points rotated by an arbitrary angle t. And so we can actually make that a function, say, rotate square of t, and we say, oh, okay, so we make it a function, and then time for a story that Jedi won't tell you, that we're not going to include that colon right there. Because if we do, then every time this function is called, this mapping will take place. And we don't want that to happen every time. So Mundulator says, it seems only the corners rotate in the circle. The points of the sides of the square rotate in small circles, as they're connected to the points of the circle, which is not rotating. Yep, that is exactly right. And so that's actually exactly what we'll be recreating down here in the accurate recreation. But right now, we're kind of revising and fixing the code to recreate this animation over here on the left. We'll get there, I swear. Okay, but so in just doing this, just the equal sign, we can say, okay, for any value of t that we give it, replace that into this evaluated expression on the right. So we don't have to do this mapping every time. Well, mapping and rotation. And so, practicing prudent programming, well, we can actually just join or merge these cells, because we have our clear of rotation, or rot square, down here. And so, okay, well, we don't want to look at all that. So we can just say, no, I don't want to see it. Okay, but now, what does this look like? So let's just come over here and say, grip. And so let's just copy paste that graphics. Okay. For MIDI it says, what does clear do? You put it before the rest of the code. That is correct. So I'm practicing prudent programming, as one of my professors used to say. We include the clear here, and it's clearing each of these symbols in order to make sure that, for whatever reason, Mathematica does not try to mix definitions upon reassignment. Okay, so Lunch Nest says, so the points are just rotating around circles between the inner and outer circle of the square. So the points are just rotating around circles between the inner and outer circle of the square. I'm not sure I understand. Let's make the music down a little bit. So you can draw a circle around the square and one on the inside. Yes. Yeah. Yes, you could. Yes, you could do that. Okay, but anyways. So yeah, let's rip this graphics kind of module and say, okay, so let's make a circle, and we want the points on the circle to be orange, and then we want to say, okay, put a point at each of the points on the circle. And then down here, well, so let's go step by step. We can just do that and then go like that and say, oh, hey, look at that. And we also specify that our background to be whatever this color is. Well, it's that. And we can actually also say to give us a little bit of an extra little bit on the sides. Just some breathing room. Okay, so we've made our circle. We've made our outside circle. I would say that's maybe the easiest part. Yep. And we're able to do this because the developers of Mathematica and the Wolfram language made the functionality of point be able to, or made point be able to kind of take a list of points and put a point at each of those vectors in the list. Okay, but then going down, and so now we want to put in our square, and so we have our square points, and that is just a list of points. And so what we want to do this is jazzy. Okay, so we rotate point T. Okay, I was doing something else here originally, but I don't want to do it that way, so we're not going to. And we can just delete that because it's still over here. So what we're going to do is we're going to say, okay, make each of these points yellow, and then we're going to say point at square points. And what if we just say that? Oh, it doesn't like that. Oh, that's because we included our lines command, which we don't want to do yet. But what if we just do that? Hey, look at that, everybody. We have a square of yellow points, and it's beautiful. What a lovely day. Okay, but now the hard part. Making the lines go from the outer circle to the inner square. And we'll get to the animation part of it. Actually making it rotate, I think, in the end. Yes, Doe. Haha. We've done it. Okay, so now we make some lines. And the beautiful thing here is that I'm actually going to delete that. And so one of the very nice features of Mathematica is this nearest function. So we can say, okay, what does nearest do? Well, if we give nearest a list of points, or a list of elements, that's very hard for you guys to see. Scroll up. So we can say, okay, given a list of elements and a point x, or an element x, this function gives the nearest one of these elements in the list that is nearest to x. We can also say, and then there's a bunch of other functionality that we could go into to kind of make it do exactly what you want in different circumstances, but none of that really applies to us. Except maybe this last one here. So this is a functionality that was introduced in Mathematica 10 kind of the ability to do operator forms of functions. And so I believe we are going to use that. And so basically what we're going to do is we can zoom back out a little bit, is we can go up here and say, well, let's work with 1 first. So let's pick just the first point on our circle, and that's, go figure, 1, 0. That one. And we say, okay, what is the nearest point for, what is the nearest point on the square closest to this point on the circle? Okay, so from it says, how long have you worked and studied with Mathematica? So I picked this up in early 2015, and I used it pretty much every single day for a long time, and then maybe faded off when I left school for a bit. But now I picked it back up again. I was really into answering Stack Exchange, Mathematica Stack Exchange questions for a long time. I gained some reputation over there. I think, what am I at now? 5,554 reputation on the Mathematica Stack Exchange. And yeah, and I really like doing those because it gives me a chance to kind of problem solve and just think about how to implement the features and functionality of Mathematica in different ways. I also have done theoretical physics research using Mathematica, and that was a lot of fun. I spent a few years doing that. Need some water. Thanks, chat. I could feel you kind of redeeming the non-existent hydrate channel points reward. So I thank you for that. Okay, but now we say, so this is, remember, circ points is a point. And so we say, oh, but nearest doesn't take, well, we want nearest to think of that point 1, 0 as, or wait, no, I'm doing this backwards. So this is the point on the circle, which is this one. And then we want to know, out of all of the points on the square, which one is closest. And so this point on the circle is actually the second argument in nearest. And, well, we can just say, we can just give it the list of square points. And look at that. It spits out this point right here. In the event, the reason why it gives us kind of these outer brackets is because in the event that 2 points are equidistant from this point on the circle, it would give both. And so, but what if we don't want the first point on the circle? What if we want the second point? And so, okay, well then that's this one, and it gives us the point. I believe that's this one. And so we can go around and do that for every point on the circle. And it'll give us the nearest point on the square. And so what we can do is, I wonder. I don't think so. Well, maybe. Probably not. I mean, maybe? So So I'm thinking, can we maybe use some undocumented functionality, unless I'm missing it in the description down there at the bottom, to say, okay, for every point on the circle, give us the nearest point in the square. And I believe that is actually what it's doing. And so each of those should correspond to 1 point. And so we can say 33. So I think it is actually giving us exactly what we want. In this nice, compact little piece of code right here. Any other questions? Feel free to ask at any time. Those of you that are still here. Okay, so now we have the points. Now for each point on the circle, we have the point in the square to which it is nearest. Dough is here, is here. Okay, and so now we can say, and since there will, well, except for the corners, we can say, so if we look over here in the animation, that the corners of the square actually have 3 circle points that map to it, in terms of which square point is nearest. And so we can say, we can map our length function over that. And so it says that each of these is actually only 1. From Idiots is trying to be here. Well, I appreciate it. So maybe there's something up there. Yeah, the syntax is very different from Python, from Idiots, which is why I think I like it. It looks like you all can hear that dog barking in the background. Hopefully it's not too annoying. So this is this one. Then say 1, 2, 3, 4. So 1, 2, 3, 4. So this is right. Yeah, so this corresponds to, well, so these 3 elements right here correspond to these 3 points on the circle, and they all, the nearest point on the square to each of these is the same point. And so that is, well, correct. Just as kind of a verification. And so now what we can do is, so now this is the tricky part. That actually takes some thinking. I'm not feeling this music. Okay. So, basically for each of these, what we can do is, well, yeah, we can go like that and say, yeah, so now we can say, okay, transpose. And so now we have, okay, so what did I just do? What this is saying is that, what this is doing, what this kind of 3 @ symbols and a join is saying is that in this piece of code, it's saying basically to get rid of each of these outer brackets in each that contain each point in this list. I don't know if that makes sense, but that's what it's doing. And then so then we just have a list of points corresponding to each point on the circle. And so we have that list of points, one for each point on the circle, and then we have the exact point on the circle, and so we can make a list of those and then transpose it. So now we have, this list had this sorry, what am I trying to say? This list of 2 points corresponds to the point on the circle and the point on the square closest to this point. And so we could do this in using a table or some kind of iteration method, but I think I'm going to keep it like this, even though another way may be more procedural and maybe readable, but doing it this way really allows us to use the functional nature of the Wolfram language. Yeah. So we can actually also come over here and say, we don't want to look at cosine of pi over 16, we just want a number. And so we can force the numerical representations of those. Okay, and then, so now that we have a list of pairs of points, we can say, oh, I want a line to kind of just be from each of those points to those points. And that's not going to do anything because we need to put it in a graphics. But we can do that up here. So we can say, come up here, and we say thickness 0.007, because that's my personal preference, and line at that list. And we also want the line to be this color. And look at that. We did it. Now we just need to rotate it. Can I get some hoorays in the chat, please? Hooray! I know. Effing poggers, right? Okay, and now, how do we rotate it? Well, using our rotate square function, it shouldn't be too hard. But so, what we're going to do is copy this whole thing, delete this output, and then make a new cell for our manipulate. So in case this doesn't work, we still have our still, our snapshot. And so what we can do is we wrap this whole thing in a manipulate, and so for idiots, it says physics-based rotation to make it harder. What do you mean? Rotation based on Lagrangian. Well, these points aren't exactly in a potential or experiencing any sort of... well, I mean, at the very least, these points do not obey the principle of least action, so... but Mathematica does have kind of Lagrangian... or what's it called? Mathematica can do Euler-Lagrange calculations. It's very interesting. As in, like, there's just functions for that. But that's not what we're doing here. So, okay, so how do we rotate it? How do we let it rotate? Well, what are we rotating? We're rotating the square, or rather the points on the square, or rather the square points. And so, all we need to really do to rotate it is just mess with this, is mess with our square points. And so, yeah, and so instead of square points, we're actually going to just replace that with our rot square. And recall that the rot square of 0 is just square points. And so all we need to do is that, and then we can say, okay, manipulate or kind of evolve t from 0 to 2 pi, because we want to rotate the square around the full circle. And so what happens? And so another kind of thing that I always like to do is save the notebook before any new manipulation. And so what we're going to do is we're going to come up here. We're going to copy that title, and we're going to say, go like that, and then look at that, that's saved. So in case it crashes, we'll be fine. So then we save, and then we run it. And, well, let's make this an animator. And, okay, chat, what did I do wrong? I know what I did wrong, but what do you think I did wrong? I'll let this go, so we can just look at it. Anyone? You only put rotate square in line. That is exactly right. Yep. I did not tell the graphics command to actually rotate the points, the rendered points. A rotation is going in the negative direction in the original. Right, and so all we need to do is say negative t. Well, we also copy and paste that to that. And what do we get? Look at that, chat. We did it. Can we get some more hoorays in the chat? Oh, wait, no. Huzzahs. Can we get some huzzahs? Yay! Huzzah! It's very fast, though. And look at that. We have crawling connectors of nearest neighbors. Oh, Eric, you're still here. And look at that. We have crawling connectors of nearest neighbors. And guess what? That's the title of this stream. Oh, my God. We did it, fam. It's beautiful. And see, and now look how much nicer this code is compared to this code. Really, this and this, where we have this and we're kind of using our listable features of nearest and how we've defined our kind of sets of vectors and our rotations, instead of having a bunch of kind of manual stipulations of where the points are. We just use some math and did some rotations on one set of points to get the full square. And we made our beautiful little thing in much more nice compact code. Not that it runs any faster. Any noticeably anyways. I mean, for many it's kind of like the energy, what is it? The energy of a particle in an electric potential. You kind of have to integrate from infinity. And so in the same sense, there is a lot that goes into being able to do this kind of on the fly. I've used this program and this language, and I think this way mathematically and just on my own way and through practice. There's been a lot of work and effort and time that that allows me to do this kind of thing. And yeah, physics, it's like a centipede. That's kind of what I think of when I look at it. Now make the outer circle rotate counterclockwise. Okay, let's do it. That's a good idea, Mindulator. Okay, so let's nuke that. And then, well, for each of these, we can say, we don't have a dedicated function for this, but we can just say rotate matrix, T. Let's start with the same frequency, and then we can move to, or having the outer circle. Well, actually, that's not hard. Let me just say omega. Yeah, and then, well, now we can just come down here and say omega from, well, let's say omega is, well, actually not 0, 1. Or wait, no, omega is, yeah, no, 1. Yeah. 1 angle per time. But then we can say, make it go from -1 to 1. Okay, and before, of course, we hit enter, I'm going to make you wait for it. So rotate circle with rotate a circ of t. I mean, yeah, pretty much. It's the same idea of what we did here. Rotation matrix over a certain angle and mapped over the points that constitute, or that compose kind of our shape. And so that's what we're doing here. And actually, what we can do is we can make this even cooler. Well, let's be good programmers and say omega circ and omega square. And so now we're going to say omega circ and omega square. And so what's going to happen? Whee! Oh, see? Okay, chat, what did I do? these lines are not going to the points. How do I fix it? What did I forget to do? I'll give you a hint. You've already answered it. Why is this so fast? Oh, that's because that's a list animate. Oh no. What'd I do? Abort. Oh, I know what I did. Yeah. Yep. This is me. This sound you're hearing is me mashing Alt period, which is the keyboard shortcut to abort the operator or the evaluation. We can also go here and kind of... Okay, there we go. Woo! Sometimes it doesn't like to put the errors in the kind of console and instead puts them in the notebook. So we can delete all those. And the reason why I did that is because I've used the same names over here as over here. And the default setting in Mathematica is that basically variable names are shared between notebooks. But since we have done prudent programming and included a clear statement at the top of our kind of variable declaration cell, we can easily say, okay, let's go over here, run this declaration cell, and then run this code to make the original animation, even though we don't really need it anymore. And then it takes a second because it's rendering all of the graphics instead of one at a time. And then we can come over here, and then for the same reason, we can, because we included our clear statement, to unset all of the definitions made over here. Now, ooh, this is a groovy song. I think I like those levels. And, well, actually, yeah, just that. And so now we can come over here, run that assignment cell, and then come down here, and then get back to the question. And for MIDI it says, in line, it's still the old circle points. Yep. So we go to our lines, and we say, okay, do. And right, we're still giving the original, we're having our lines kind of look at the original circle points instead of the rotating circle points. So now we can just kind of copy that. And bad practice, but you know, just to kind of get a prototype working. Whoa. I wasn't expecting that, but that looks really cool. Are y'all seeing this? Look at that. It's like a camera aperture. I think that is actually much cooler than anything that I was planning to make. Which is not the first time that's happened to me. Look at that. Wow, I could just watch that all day. It is like the Stargate iris, yeah. Close the iris. Spirograph fun. I actually have another project doing exactly that we can go over sometime. You can actually get a peek of what we could be doing on that project on my website, and that's linked down in the description down below. I wonder, I should have it on my socials. So on my website right there, Science for the Busy. It's in the blog tab. You can check it out and see a lot of fun spirographs that I've also made with Mathematica. God, this song is good. Smooth jazz. But now, if we do slow this down, we can see that our points are not actually our circle. The starting positions of our lines are still not where they need to be. It's not finding the nearest, though. Yeah, I did something wrong. Still cool, though. It finds one and sticks with it, yeah. Okay, so what is happening? Okay, so the square is rotating. The circle... Oh. The square is not rotating at the right frequency. There you go. Well, almost. We didn't fix our initial problem. It's still the lines are not going where they need to be. Yeah, I think it was the combination. Nope. Okay, I think that code is just wrong. It looks very cool, but that's not what we're trying to do right now. What am I doing? Line. Oh! It's this one. This is the circ points that I needed to modify. Or both, actually? Yeah. Yeah. Okay, so what we're gonna do is instead of that, we're going to take that and then no, that's not what I wanted. Also not what I wanted. I'm gonna take that and then we're going to say go over there and then make this a pure function. So there's that, and then there's that, and then I'll make it t-circ. And then we're going to close the transpose and look at a super cool thing. There you go. Okay, well, let's slow this down. Yeah, can we get some yays in the chat? And so the beauty of this one is that since we made our frequencies of rotation variable, we can actually change it. And so as we move this one along, you can actually see the points moving because it's updating kind of where they are as I move it along. And so we can say, okay, what if the square and circle rotate at the same rate, except in opposite directions? Now what if they rotate at the same rate in the same direction? Look at that. Math works. Isn't math beautiful? But what if the circle is slightly off. Now we just get an almost chaotic looking thing, seemingly random. Okay, so Doe asks, how many circle points do we have? Square, can Mathematica, gonna start abbreviating it, yeah, count those up quick. Yes, it can. So the number of circle points we have, so we can say, okay, what's the length, or actually, we can either say, okay, we can map length over circ points and square points, or we can say dimensions, circ points and square points. And so, well, they don't have the same, right? Yeah, so we have 32 points on the circle, or 33 points on the circle, and 32 points on the square. So this is actually an application of, or we can invoke the pigeonhole principle here, the pigeonhole principle, and say that, okay, every point on the circle is attached to a point on the square. And so since there are more points on the circle than there are in the square, there exists one square point that has at least two lines connecting to it. I think that is right. So dimensions only gave me one number because dimensions only gave 2 here because there are 2 elements in this top level, and it didn't give a second one because circ points and square points do not share they don't have the same length. So if I wanted to say append square points with 1 or a, then now there are 33 points in this element, or in this kind of row. And so, okay, it's dimension says this array, this list of lists of lists or whatever, has 2 elements in the top level, or 2 rows, and then 33 columns, or 33 elements in the next level down. Yeah. Okay, but I'm going to leave for one hot second, and you guys can chat amongst yourself and watch that, and watch its earlier predecessor, and watch the original we're going to try to recreate. Okay, so I'll be back in 1 second. Hello? Hello? Anybody still there? Let's see, has this functionality been... Hey, look at that. Congratulations, Physics OH. You have been promoted. Or should I say Psychics? Psychics O. Can we get some Psychics O in the chat, please? Echo? Oh, I see what you're saying. Yeah. Okay. So that's super cool. That was a really good idea. Mindelator. See, to make the circle spin too. The other way too. And yeah, we can make it have variable speeds. We have now successfully created a community with our greater than 50 followers. And I think however many people chatting at one time. We're moving up in the Twitch world. On our way to affiliate. Then we can get some channel points and some other stuff. People can subscribe if you want to, for some reason, give me money. I certainly won't say no. But yeah. How y'all feeling? You want to see more? Should we try to actually recreate this thing over here? There's great potential for learning and science communities on Twitch. I agree. And a lot of that potential has been realized so far. With people like Professor Melko and Professor Peter and Gathwiggle, Dr. WD40, Rocket Sage, Uncle Bill. Definitely no one in the physics community has taken up the call to produce good content. And yeah, and the other ones too. Tayo Inu, I like him. He's pretty new, and he's been doing very well. Also, shout out. We do have a shout out ability now. Oh, that's interesting. It doesn't filter it. There we go. So yep, shout out Physics OH. They're doing cool stuff. Look at that. You're my first shout out. I hope you know. And I highly suggest them if anybody doesn't know them. If you're here from, say, Reddit r/Mathematica, I highly suggest Physics OH. They do cool physics stuff. Today, what did we do today? Today was a building stream. We got some sparks out of a Tesla coil. And Physics is celebrating his departure from the restaurant industry. But he totally blew the leaving ceremony, if that's what you can call it. I kind of like this one. Focused on physics now. Yep. And I mentioned before, maybe for my viewers out there, maybe you all we'll see one day a pseudo collaboration or a relay talking about a physics concept on Physics OH's channel and then a computational implementation over here. Look at that. Look at that. It just works. Isn't that nice? But now I'm curious. What did we do before? What was it? What was that really cool piece? It was having this. Yeah, the starting positions of the line, or the outer positions of the lines be fixed. And what was that? Was that just circ points? Yes. And then what if we just got rid of the circle? I like that. There we go, chat. Here's something else we can do is, well, here's what we can do. We can so this song you're hearing right now, I'll boost it up a little bit. This is a song from the game Jet Set Radio Future. It was composed by Hideki Naganuma, and it's one of the best games ever. And I will stand by that statement. But anyways, so what we can do is we can put things back the way they're supposed to be. Go like that. And slow it down, because that hurts my eyes. And then we can take another one. Actually, no, you know what? We're going to do it. We're just going to do it. What we can do is... No. We can just throw this whole thing in an if statement. And say, else... Oops. And then we can take out our thing. What is it? No, circ points. And then we can come down here and say Spyro takes true and false. And then we delete all output, save in case it crashes, and go like this. Oh no. Spyro equals false. Well, that's not what I want. What did I... So let's start with true. False, false. Oh. What am I doing? So this is a regular one, and then we say, no, we don't want that. We want the cool version. The cooler Daniel. And we want to get rid of this. We can really actually just yank that. And we can say, boom. And now we can just toggle back and forth. Gotta run study group. Well, thanks for hanging out, make it work. Love to have you back whenever you have the ability. I actually haven't been paying too much attention to chat. Alright, physics. Good old Psychic Zo. Already I'm logging off for the night. Have a great stream. It's been great so far. Thank you so much. It really does mean a lot. You know, the few of you that do like to come over and stay and chat and watch me kind of dink around, it makes me feel good. I like talking about this stuff, and I'm doing this for you guys, and I hope you learn something and enjoy the content. And so I hope everybody is just having a good time overall. Alright, but yeah, make it work. Thanks for hanging out. Good luck in your study group. So Mindolator, good job. Way to go squaring the circle. I mean, yeah, it's like, why didn't those 18th, 19th century mathematicians just have Mathematica and then also redefine squaring the circle? But this is super cool. I think this is way cooler than the other thing. This kind of spirography thing. Just look at it. It's so cool. Definitely gonna make a GIF of that and post it around later. Let's see. Accidental beauty. Yep. Ask a Zen Buddhist what this animation means. They'll say... there's resonance in everything. There you go. But yeah. I think this is actually where I might call it today. It's been a good 2 hours or so, I believe. Let's see. Uptime. 1 hour and 53 minutes. Alright, I'll give you guys... Well, does anybody have any questions in these maybe last few minutes? For me, or about Mathematica, what you can do with it. I'm happy to answer anything. Almost anything. Tell your friends, tell your family. No? No questions? Okay, well, if everybody's good, yeah, thanks for hanging out, and if you're not already in there, come on over and check out the Discord. We've got a lot of questions, but they're all so basic, so I'll just check out the tutorials. Yeah, from idiots, there is also, I have my, I need to make it, probably should make a command for this, but on my website, I have written guides for Mathematica. They also include exercises, and I think that would be a great place to start if you were so inclined. On the website, under the Mathematica tab, they're right there. And I've made them freely available for all. Okay, everybody. Don't have too much fun. I hope you enjoyed stream. I know I did. And hope you come back next week. Alright. Good night, all. Enjoy your spiographs. Oh, wait, no. I lied. Is there anyone we can raid? Is anyone on? Ooh, Ty's on. Lantern is also on. Ooh, Ty's on. Oh, look. Physics OH is hosting me. Let's see. Yep, Laboratory 24 is also on. Alright, do you want to go to Tayo Inoue? They're talking about math over there. That might be where I'm headed after this, actually. Or do you want to go to Lantern Noir, who's playing Minecraft? They're very chill. He likes talking about history. He's a math teacher. Tayo is he has a math PhD. He's a faculty at somewhere. He's currently on sabbatical, and he's kind of doing the same thing here. Thank you for the follow, Mind. Hope you come back next time and enjoy the stuff. And he's pretty cool. He's very chill. Alright, we'll flip for it. Actually, you know what? Let's go to Ty. Well... Actually, you know what? No, let's go to Lantern. Let's spread the love. I'd raided Ty last time, so... Let's go raid. What is this song? This is nice. Lantern Noir. I believe that's how you spell that. Alright, everybody. The few of you left out there, I'll see you next time. Good luck.
Oops. 1, 2, 3. Alright, so up.